Good morning, everyone. Thanks for being here. I see that there are 13 of you, and that's really wonderful. This is perfect. This is a big day and an ambitious day, and I sort of was thinking, like, how much should we cover? And I'm going for the more ambitious plan. So I hope that this isn't too fast. I really want to give you like a solid introduction to calculus. But note that, yes, it is going to be maybe a lot to take in. So this lecture will be recorded, and of course there's no homework. Like, obviously, I can't give you homework at this point, so don't worry if not all of it clicks. But really, I'm going for enjoyment over mastery, in line with, I think, my attitude towards many other things. So yes, thank you for being here, and let's get started. So, and I should really say, for anyone who is just joining, like, this is really geared to the 11th to 12th graders. So if you're a 9th or 10th grader, this really will probably be a lot. Okay. So this is an introduction to calculus, and I'd like to start with something rather simple. Okay, people, give me just, okay, you can all see my email. Okay, don't worry about that. Okay, so let's start with a function that you all know very well. Y is x squared. This is the quadratic, and I'm going to plot this. Okay. You all know that this is what y is x squared looks like. Okay, and I've given some points here, -2 for the x values, -2, -1, 0, 1, and 2. Right, and these are the corresponding y values. You could just plug these in here, and you will get these y values. Yes, and so I think we did this earlier. We computed what the differences in the y values are. In other words, we found the slope between each point, right? In a sense, we computed these differences and we divided by this difference. So this difference, right? The difference between 4 and 1 is what? Can someone tell me? You can also just say that yeah, it's 3, and because I'm going down, it's actually -3. So yeah, you're right. When I asked what is the difference, sure, but I have to add -3 to 4 to give me 1. And if I divide that by the corresponding x difference, in other words, if I take the slope, between these 2 points, the delta y over delta x, it'd be -3 divided by 1, because this is changing 1. So -3 divided by 1 is -3. And similarly, what do I need to do to get from 1 to 0? What do I need to add, so to speak? Shout it out. -1. Okay, sure. Sorry, and my volume was down, so I can't really. -1 is right. And what is the change here? This change is also 1, as always. So this is -1. What is the change from 0 to 1? 1, good. And this is also divided by the increment in the x, delta x is 1, so that's easy. 1 divided by 1 is 1. And what is this change?
1, 3.
From 1 to 4? What do I need to add? 1 plus
3.
1. Yeah, good. Okay, good. Okay, good. So now we have this notion of this is the slope. So remember when we were doing linear functions, how the slope was a constant? Well, now the slope of this parabola is clearly not a constant, and I can plot these points that we got, right? So -2. So the x values are the same, right? Let's see. Actually, okay. So people understand that what I just computed is the slope between each of these points, right? And I can't really. What I can do is you can plot if you wanted to plot this what I'm calling y prime, I would have to use intermediate x values, right? Because and those intermediate x values would be like -3/2, -1/2, 1/2, and 3/2. So I can plot it if you want. I don't want to take too much time on this, but negative 3/2, negative 1/2, 1/2, 1/2, 1, that's somewhere here, and then 3/2, 3, that's somewhere there. So this is what I got. So this is what I'm calling y prime. That's what this dash means, y prime, right? And now what if I do the same thing again? So I'm asking you, what is the difference between negative 3 and 1? In other words, what do we need to add to negative 3 to give me negative 1? Someone. This should be ridiculously trivial.
2.
2, and what do I need to do from negative 1 to 1?
2.
2, and what do I need to do from 1 to 3?
2.
Yeah, good. Okay, so, and now I can plot these as well as a function of these, and obviously I just get a constant. And I should have done this in another color to indicate. So this is in red. And I got this line 2. So the slope, in a sense, the slope of y, the slope of our original function, y is x squared, is plotted in blue, and that is what I'm calling y prime, right? And the slope of y prime is plotted in red, and this is y double prime. And why am I using this notation? It actually turns out that what we've just plotted, these things are approximations of what is called the derivative. And so we're gonna formally introduce this idea of derivative, but you can think of the derivative as sort of the instantaneous versions of what these things, right? Here we've taken finite differences, right? We've taken a big difference from, see from negative 2 to 1, that's a big difference. It's a finite difference, right? That's why we use this delta, right? It's a finite difference. And similarly in the y range, we've taken finite differences. 4 to 1, that's a big difference. That's why we use this delta. When we talk about derivatives, we're taking infinitesimal differences between values. And so if I had a really good computer and I put in negative 2, and then if my next value was negative 1.999, and I found the associated y value, and then I took that difference, that would be closer to the derivative than just the slope. But what I'm really telling you is that you can think of the derivative, this is the first derivative and this is the second derivative, you can think of these things as sort of a generalization of this idea of slope that you learned in middle school. Right? That's really what we did. We just took the slope of this to get this, and we took the slope of y prime to get y double prime. So this is an introduction to the idea of the derivative. So y prime is a derivative of y, this black function, and y double prime is the derivative of y prime. So any questions thus far? Okay. So derivative is, you can think of it as the instantaneous slope. So here, these were not instantaneous slopes, but so this is not exact, but you can think of these things as approximations of the derivative. And again, y prime is what we call the first derivative, y double prime is what we call the second derivative. Can someone tell me what y triple prime is equal to and what it would be called, looking at our data here? What would y triple prime be? What happens if you take the difference between all these things?
It would just be a vertical line.
It wouldn't be vertical. Can you tell me what the values would be? What you need to add to 2 to get 2?
0.
Right? And dividing, 0 divided by anything besides 0 is 0, and you're dividing by 1. So all of these, so all the values of y triple prime are 0. So y triple prime is just this line, right? It's the line y equals 0. And so so y triple prime is 0. And what, can you use your imagination and tell me what it would be called if y prime is called the first derivative and y double prime is called the second derivative? What is y triple prime called?
Third derivative.
Yeah, it's called the third derivative. And this goes on and on. And so to answer this question, y triple prime is equal to 0, and it's called the third derivative. So you can take an infinite number of derivatives, but eventually, at least in the case of things like x squared or x cubed, powers of x, eventually you'll get to a boring result. Eventually your derivatives will become 0. So, okay, so this is sort of big picture, and I know I'm really throwing you into the deep end by using these big words like derivatives and, instantaneous. So this is just an introduction, and we're going to formally develop our idea of what the derivative is. And I should have probably introduced this better, this entire field of calculus. Really, what inspired calculus was problems in physics, right? People wanted to know, if you throw a ball, what is the point at which the ball attains its maximum height? What are the effects of things like viscosity or air drag, things like that? These are questions that Newton wanted to answer. And this notion of calculating the instantaneous slope, this is so much more precise than just slope, right? A finite difference slope, the type that you learned in middle school. And so that's really, we want to analyze functions, right? And we want to analyze how they change. And that is really what we're covering today, this field of differential calculus. And we're only skimming the surface, but I know I'm throwing you in the deep end. Let's do the same thing with y is x cubed, okay? So I've given you some x values, and for the sake of time, because there is so much to cover, I'm going to kind of go a little faster in this example. I'm assuming that people will follow along if I fill in this table. So for -2, I would have -8. Look, I'm just plugging in the x values into this equation. For -1, I'd have -1. For 0, I have 0, 1, and 8. Okay, and I can plot these things, and I would get something like that. Okay, and now can someone tell me what these differences are? Fast.
7.
Good.
1.
Good.
1.
Good.
And 6.
Yep. And now can someone tell me what these differences are? It can be the same person. It's okay.
7. All right. 6.
-6.
-6. Sorry. Yeah. 0.
0.
And then 6.
Good. And now can you tell me what these differences are?
6 and 6.
Yes. Good. And so I was a little more sloppy here because I didn't. I didn't divide by the corresponding x values, but the x values are changing by 1 each time. So these are actually the y value. These are actually the correct values. Okay, so I hope you're following what's going on. And you can see, again, if I took the fourth derivative, right? And usually people don't use 4 primes. Usually people will use Roman numerals, and they'll write that, IV, fourth. And can you tell me what that is?
0.
0, good. So here's your, again, I said that most, all the powers of x, their derivatives will end up in 0 at some point down the line. So I'm gonna plot these things. So I'm gonna plot y prime. So y prime is negative. So -2, 7. That's somewhere up here. I'm gonna do this in blue. Okay. So -2, 7, -1, 1, 1, 1. So it looks like this. That wasn't too good. Sorry. That was worse. Okay, it looks something like that. Y prime, -6, -2. That's like, sorry, -2, -6. That's somewhere down here. -2, -6. 0, 0. So it goes through the origin. 6, 2. So this is clearly a line, right? And then I should have used a different color. Sorry, people. And then the third derivative is a constant at 6, right? This is the third. And the fourth derivative is 0. So you can start to see sort of what's going on. You start with a complex shape, and then you take the derivative, and you get a little bit more simple shape. And you can tell that the derivative here, this looks like a parabola. This looks like something like x squared. And then the derivative of that is, a line. So it's something that goes as x, linear, and then something that goes as x to the 0, or like proportional to a constant, right? So you can tell that upon each derivative, things seem to be getting simpler, so to speak. Your function loses a power, right? Here you had power of 2. So the original function was power of 3, right? And then you got power of 2. So you can see sort of the general trend, and this is really what I want to highlight. So does anyone have any questions about this sort of vague introduction of what the derivative is? Any questions? Okay. I'm going to invite Dr. Lee to this meeting. He just texted me. So give me a sec, people. This is a mess here. I have the Zoom windows open. This is other email. Sorry, people. Okay, so think of, do you have any questions so far? I don't know if people are taking notes. Any questions thus far? No. Okay, no questions. So how can we formalize this result of the instantaneous slope? Well, we can appeal to this thing called the limit, the notion of the limit. And this is, and when you take calculus, this is sort of how your class will start. What is the limit? A big concept in calculus is the idea of the infinitesimal and the infinite. So you'll get very used to writing this symbol, infinity. And the limit is a way of thinking about infinity. And it's a way of thinking about also the infinitesimal and small, small changes. And we denote the limit using the letters lim, lim, almost like that. And the limit asks you often what a function equals as you approach a certain value. So I know this is all very abstract, so let's just let's just jump right into it. This is a classic question, like, what is the limit? This is how you would read this. What is the limit as x approaches 1 in the function 2x? So I'll draw 2x. So this is like my function, f of x, right? I'm going to draw it. It looks like this, yeah? And you know that there are points here, 1, 2, 1, yeah, 1, 2, I can do this, 2, 4, so on and so forth. So can someone tell me what the limit as x approaches, so here's the point, x approaches 1. So as I approach x is 1, what does my function value equal? What is the function value?
2.
2. So the limit as x approaches 1 of the function 2x equals 2. That's how you would read this statement. So this is an obvious claim, right? Because there's nothing really fancy going on here. So you don't even need really the notion of limit, but I'm just, again, just introducing you to the limbo. Can someone, okay, so I'm gonna draw x cubed. So this is another function. And this is saying, what is the limit as x approaches 0 in the function x cubed? And so here's x cubed. This is kind of what we just drew. Sorry, that wasn't a good graph. It wasn't much better. But anyway, here's the point, x is 0. Can someone tell me what the function value equals as x approaches 0? Look, I'm gonna approach 0. What does this function value equal?
0.
0, good. As straightforward as it can be. No matter which side you approach it from, right? The function value equals 0. So yes, the limit of x cubed as x approaches 0 is 0. Can someone tell me now, I'll graph the sign of x in case people forgot. Looks like this, and it goes on in this direction. Can someone tell me what the limit as x approaches 0 of sign of x is?
0.
0 again, good. So this is, you can see that this is really not hard, right? Basically all you're doing is you're computing sine of 0, right? You're just putting in, you're just putting in the value that it approaches into the function, right? And you're telling me the answer. But I'm appealing to the graph because that's what we'll have to do when things are more sophisticated. Like in this case, what is the limit as x approaches infinity of e to the x? And I'll draw. Okay, I didn't. Okay, let's do this example. Here's e to the x. It grows and grows and grows. So as x approaches infinity, that's this direction, right? So as you go more and more in this direction, first of all, does this function approach a certain value or does it keep going?
Keeps going.
It keeps going. So what is the limit?
I guess just infinity, right?
Infinity, it's infinity. And actually when I wrote this question, I meant to ask a different question, and I'll just write that here. What is the limit as x approaches negative infinity? So as you're going in this direction of the same function, e to the x.
Is it 1?
0?
Yeah, it actually is 0. And if you remember, the asymptote of an exponential, of the parent exponential, is at the line y equals 0. So this is 0. So yeah, so one side it's bounded, so to speak. One side it has, you know, a definite value of the limit, and the other side it doesn't. So now you can start to see where you can't just plug in, you know, you can't just plug in the value you're approaching into the function. You can't evaluate e to the negative infinity. You know, you can evaluate e to the negative big number. You can evaluate e to the negative 1 million, and you can look at a trend that would be close to 0. But you have to sort of use your intuition to answer these types of questions. Okay, let's do just a few more of these. What is the limit as x approaches 0 of the natural log? And I'll draw the natural log for you. Looks like this. So as x approaches 0, what does the function value approach?
I'm thinking negative infinity.
Negative infinity, good, because it keeps going down and down and down to the depths. And can anyone tell me what the limit as x approaches infinity of the same function is? So as you go this way, does the natural log, does it ever level off? It actually doesn't. So what does the limit equal?
Infinity.
Infinity as well, yes. Good, so I hope this is making sense to people. I'm just sort of running through examples. Let's do one more. Here's the limit as x approaches negative infinity of 1 over x. I'm gonna tell you 1 over x looks like this, roughly. It's like a hyperbola. And so as x is negative infinity, that's going in this direction, what does this thing equal?
0.
0, good. So I think you're getting, so at least, I don't know who's speaking, which is bad because you're participating a lot. Whoever's participating is really understanding this, but I hope this is making sense to more than just this person. Okay? Good, okay. So we have this idea of limit, and all of the above functions that we did, you know, we looked at the limit of values as y is x squared, y is sine of x, and this last example, y is 1 over x. All of these things are differentiable. They all have derivatives. And the limit actually helps us define what can have a derivative and what cannot. And central to this idea of what can have a derivative and what cannot is the idea of continuity, whether a function is continuous or not. So if a function looks like this, if it jumps, this kind of thing is not continuous, and therefore it actually does not have a derivative. A function that's nice and smooth, these types of things do have derivatives. And there's a formal mathematical definition of continuity, and it uses the limit. And specifically, that definition is that if the limit from the right-hand side, and that's denoted by a plus sign, equals the limit on the left-hand side for all points on that function, then the function is continuous. So I know that's sort of a mouthful, but basically what it's saying is that take the point x is 0 here. Because the function approaches x is 0 from the left-hand side and from the right-hand side, in other words, because the limit of this is how you denote approaching from the left-hand side of the function, because this equals the limit of the function from the right-hand side, denoted by the plus sign, this means that the function is continuous. Okay, and so I hope that makes sense. So this is a differentiable. This is a differentiable function. And here you can see that as we approach the point x is 0, the limit, can anyone tell me what the limit as x approaches 0 from the left-hand side of this function is? What does it go to?
Negative infinity.
Negative infinity. And what does it go to from the opposite side? Yeah, when you're coming in from the right-hand side, from the positive side, it goes to positive infinity, and positive infinity is not negative infinity. Therefore, this thing is not continuous. And therefore, it is actually not differentiable. So the relationship between differentiability and continuity is kind of subtle, and you have to kind of wrap your head around it. If a function is not continuous, then it is not differentiable. But just because a function is continuous does not mean that it's differentiable. So this relationship is I'll give you an example of that before we really formalize this relationship. So what I'm saying is not all continuous functions are differentiable. All differentiable functions are continuous, but not all continuous functions are differentiable. Here is a continuous function, right? Even at this point here, the limit of this function as it approaches from the left-hand side, it does equal the value, the limit from the right-hand side. So it is continuous, but it is not differentiable. And you can see that it's not differentiable because the slope here, right? The slope here, as you approach this point, you could think of the slope as the derivative, instantaneous derivative. It has a break, right? And so something funny is happening here. And generally, when you have sharp points in your graph will not be differentiable. So this is an example of a graph, and this is sort of, you can play with it. This is the equation for this graph, square root of absolute value of x. Generally, when you have sharp points, your graph will not be differentiable, and this is an example of a continuous function not being differentiable. So the relationship between continuity and differentiability, as I said, is a bit subtle, and it can be thought of well as the relationship between squares and rectangles. All squares are rectangles, but not all rectangles are squares. And I've denoted that by this schematic here. So in the entire world of functions denoted by this squiggly line, there are some functions that are continuous and some functions that are also differentiable. All differentiable functions are continuous, but not all continuous functions are differentiable, as denoted by the fact that this square exists in the rectangle. Okay, so I hope this analogy makes sense to people. You might want to write this down for the quiz as well. Okay, maybe even just the schematic will help you around this topic. So any questions so far about differentiable functions, continuous functions? Nothing. Okay, I hope this is making sense to people. So now we understand what kinds of functions are differentiable and what kinds of functions are not. And so now we can formally define the derivative, okay? And to do that, I'm going to appeal to the notion of slope. And can someone tell me their middle school definition of slope?
The change in y, the change in.
Yes, great. And sorry, I'm having issues with my screen. It's the change in y over the change in x. And you could think of this as rise over run, right? And this is exactly what you said. The change is denoted by the delta, right? So delta is some finite difference, right? Delta y over delta x. This is literally what you've been writing since probably 7th grade. And we want this delta, we want this entire expression to become instantaneous. So we don't want big differences, we want small differences. So if I divide a small difference divided by a small difference, I'm a step closer to the derivative. If I divide an infinitesimal difference over an infinitesimal difference, I am at the derivative. So we want this notion of finite difference to become infinitesimal. Infinitesimal means infinitely small. And so here's some arbitrary function I've drawn, f of x, right? This dashed line. And I've drawn 2 points that exist on this function, x1, y1, and x2, y2. These are the 2 ordered pairs. And we want this to become instantaneous. And right now, the way I've written this, the slope would be, can someone tell me what the slope of this line would be? Using this definition? In terms of the points?
y2 minus y1 over x2 minus
Yes, and I could have asked this to a 5th grader. So good. This is literally what you've known for a long time. And what I want to do is so this is first of all, this is what you call a secant line, and this is a slope. And I want to bring these points closer and closer together. And if I do that here, I'm going to zoom in so people can see what I'm talking about. If I bring these points closer and closer together, my secant line will approach. See here, they're even closer. And if they almost become the same point, I end up with a tangent line, right? And that tangent line is what I'm looking for. The tangent line is the derivative at that point. So what we need to do is we need to minimize this difference. We need to shrink this distance between x and y, x1 and x2 down to 0. In other words, the difference, x2 minus x1, we want to become 0. And I just showed you this idea of the limit, right? I just showed you that the limit is a nice way of thinking about what values approach when you're approaching, or what functions approach, what values functions approach when certain values approach limiting cases like 0 or infinity. We just did a bunch of examples like that. So as you said, y2 minus y1 over x2 minus x1 is the slope. And I could write that because this function is f of x, I could write y2 as f of x2, right? That's what this point is, right? This is the function value. Y2 is just f of x2, and y1 is just f of x1. Just notational difference, right? So this is the slope. And what I said is that we want the spacing. We want the spacing between x1 and x2 to shrink to 0. And I said that you can appeal to the notion of the limit, right? So again, we want x2 minus x1 to approach 0. And this is exactly the statement that I want. The limit as x2 minus x1 goes to 0 of the slope, right? So the limit of the slope as this difference goes to 0. This is the exact definition of the derivative. And the derivative is denoted by f prime of x, okay? So remember when we were talking about slopes, we had, deltas. So that we could have called this delta y over delta x. When you have derivatives, right? In other words, when you take this limit, your slopes become instantaneous, and instead of using deltas, so the limit, so to speak, of this thing, when you take the limit, sorry, x2 minus x1 is 0. When you take the limit, you conventionally replace the deltas with d's. So this is, think of, it's really, you can think of the delta itself shrinking to 0. The delta refers to a change. And when the delta shrinks to 0, you replace the delta with a d. Okay, so that's just a notation. So you can also call this dy dx, just a notation. This is called the Leibniz notation, and this is the notation that Newton used. And the Leibniz notation is actually better in many cases because it's more specific. It tells you what you're differentiating with respect to. Anyway, it's a bit more clunky, but that's just something to keep an eye out for. And sometimes you'll see the same definition of the derivative written equivalently. So this thing that I've written down here, this is equivalent to this top definition. But instead of this idea of the points x2 and x1, it just you think of this entire difference as h, so some arbitrary number h, some small number h, and you let h approach 0. And if you make that substitution in this argument here of the limit, you'll also have that this is sort of how it comes out. So literally, you can get from here to here by making the substitution h is x2 minus x1. And this is actually the definition I like. And you can see it's really the same thing. F of x plus h minus f of x divided by h. So this is just the function value at some small amount past the function value at x divided by that small amount. And letting that small amount go to 0 is the derivative. So I hope people feel comfortable with at least this definition. For the remainder of the presentation here today, I'm going to use the bottom definition because it's a bit more convenient. So do people have questions at this juncture about the definition of the derivative using the limit, the idea of the limit? I feel like I might be confusing people a lot, so please be very honest. Okay, no questions so far. Okay, so the derivative is now defined formally. And as I mentioned, when you have infinitesimal change, you can, instead of writing delta, you can write d. So the d, this is not, keep in mind, the d does not refer to, this is not a variable. Just as delta, delta is a symbol. The d is also a symbol. So when you see this, don't think of like a fraction, don't think of like canceling fractions. You don't cancel the d's, right? This is a symbol. Does that make sense to people? Just as the deltas here, you don't cancel the deltas. The delta is a symbol. Similarly, the d's refer to a finite difference. And sometimes you'll even see that people will write the derivative as something like this. So in a sense, this is like an operator, okay? This is, you can apply this to a function, right? And this is sort of its own symbol. But when you see the symbol, you should think the derivative of some function with respect to x. Okay, so this is just notation, and I hope this is making sense to people. So now that we've defined the limit formally, we can literally just start computing derivatives, and we can find some patterns that are very important. So let's start with the simplest example of f of x equals x. So y equals x, I'm calling y f of x to fit our notation. Okay, and I'm asking you, what is the derivative? What is f prime? Or in other words, what is, you could also write this as, so the notation is sort of a bit to get used to, but these are all the same thing. dy dx, that's how you would pronounce this, or dy over dx. That's the same thing as f prime of x, which is the same thing as the limit. This is the formal definition of the derivative. And so what is this? Can someone tell me, plugging in this limit, plugging in my function into, what would f of x plus h be for this function? Literally, if I plug in x plus h for the argument, what is the function equal?
X plus h.
X plus h, it's that simple. I'm just, plugging in the argument for x. And so f of x plus h is x plus h, and f of x is obviously x, so minus x. And sorry, I forgot to write the limit. So, okay. So this is equal to the limit as h approaches 0 of f of x plus h, that's x plus h, minus f of x is just x, as I mentioned, and divided by h. And what is x minus x? Someone, please?
0.
0, thank you. And what I'm left with h divided by h. And what is h divided by h?
1.
Good. So I'm left with limit as h approaches 0 of 1. And now there's no h in my statement. So this limit becomes irrelevant in a sense, right? You don't need, this limit doesn't, because there's no h, this entire thing is just 1, right? The limit, it becomes irrelevant, and this entire expression is just 1. So the derivative of y equals x is 1, okay? So I would write that down somewhere, that if y equals x, taking the derivative, you could write this as y prime as well. That's yet another notation. The derivative of y equals x is 1. Make sense? And this makes total sense, because if I write y as x, then I just have dx over dx. And obviously anything divided by itself is 1. So we could have found this result almost, naively by saying, oh, well, if y is x, then I just have the statement dx. It doesn't matter how big, if you have a finite difference and infinitesimal differences, anything divided by itself is 1. But we found it formally using the definition of the limit. Now let's do something a bit more sophisticated. Let's find the derivative of y equals x squared. So here I'm interested in finding f prime of x, which is d dx of x squared. These are, again, all the same statement. The derivative of the function x squared, y equals x squared. So here's the definition of the derivative. And now can someone tell me what f of x plus h is in this case?
X plus h squared, just x squared.
Yeah,
plus...
so I need to put in x plus h into my argument. And what happens if I put x plus h in here for x? I have x plus h whole squared. So that's what this is, right? F of x plus h, right? Do people understand this step? How I'm just evaluating what the function is? So the function itself is x squared, and I'm interested in what the function is when the argument is not x but x plus h, and therefore I need to put in x plus h into the function. I hope that makes sense. Okay, and then f of x is obviously it's given right here. F of x is x squared. So minus x squared. Okay, now I can use what we know about expanding, foiling. What is x plus h whole squared? Can someone tell me? You should know this. This is on the SAT, okay? This part, x of x plus h whole squared. Someone tell me, what is x plus h whole squared? Please. What is x plus h whole squared? People. Thanks, Aditya. Yes. Okay, I hope that the silence was not a good sign. Okay. Yeah, this is x squared plus 2xh plus h squared, and then I have this x squared here. Now, what is x squared minus x squared?
0.
0, obviously. And so I have limit as h approaches 0. And what I have remaining is 2xh plus h squared divided by h. And look, there is an h common in the numerator and denominator. See? So I can cancel by factor of h in both numerator and denominator. They cancel out. And so I'm left with 2x plus h. And this h is gone. This is just 1, right? So I've canceled this h's. Okay, and now I'm interested in what the limit is as h approaches 0. So what is this thing? What is the limit as h approaches 0 of 2x plus h? Literally, this thing just goes to 0, right? This goes to 0. This is an h. And so the answer is 2x. And so now we found the derivative of x squared is 2x. So I'm going to summarize my result here. The derivative, so if y equals x squared, the derivative of x squared is 2x. So I hope other people are helping make a sort of summary. So we found that the derivative of x is 1, and that the derivative of x squared is 2x. And we're really looking for a pattern. And to do that, we're going to take one more example. What is the derivative of x cubed? So I expect this to be a routine process at this point. So I'm interested in finding the derivative of x cubed, so y prime, or you could also write this as ddx of x cubed. And here I'm using the exact definition of the derivative, right, using the limit. And I've actually plugged it in. I assume people are understanding how I'm plugging this in. F of x plus h, plugging this into my function, gives me x plus h whole cubed. And now, using the definition of limit, I have negative x cubed, right? That's what this negative f of x is, divided by h. Now, can someone tell me, does anyone know what x plus h whole cubed is? We haven't talked about this in this course. If people don't know, I'll tell you. If you expand this, you can do this by hand, but there's a pattern. We don't really have time to get into it now, but this is what these 4 terms, if you expanded x plus h cubed, these 4 terms is what you get. And I still remember I have this negative x cubed here. So I'm not taking time to do this algebra because I'm assuming people can do that if they have enough time. Okay, so, and see, I always forgot to write limit. See, I have this limit here. I can't forget that. Okay, so now, again, what cancels? Look, what is x cubed minus x cubed? 0. So what am I left with? I'm left with the limit of x, of 3x squared h plus 3x h squared plus h cubed over h. And look, one of the h's again cancels. So look, this becomes a 1, this becomes a 2. Because see, there was an h common in all the terms. And I'm left with limit as h approaches 0 of x cubed plus 3xh plus h squared. And what is this limit? Can someone tell me? If you let h go to 0 in this entire thing, what does this equal?
Just 3x cubed.
Just 3x cubed, yeah, because look, if h goes to 0, then this entire term goes to 0. And if h goes to 0 here, obviously h squared also goes to 0. So good. So now we found the derivative of x cubed. And I'll make that statement here. If y is x cubed, then y prime is 3x. Uh-oh. There's a mistake, people. Look, I made a mistake. I miswrote 3. Look, there was a 3x squared here, and I wrote it as 3x cubed. It should have been squared, 3x squared. No one caught me. Okay, good. And so we found that the derivative of x cubed is 3x squared. Okay, and so now let's look at the three results we have. Right? So I'm saying that there is a pattern, and this is a summary of our results. The derivative of x is 1, the derivative of x squared is 2x, the derivative of x cubed is 3x squared. Can anyone tell me what the pattern is?
The exponent goes to the left. Like
Good.
it becomes a coefficient.
And what happens to the exponent itself? Like what happens to the exponent on x?
It goes down by 1.
It goes down, yes, exactly. So there are two things that, by the way, who is speaking? You're doing a great job. Who is this? Aditya. Okay, thanks, Aditya. You're the only one participating, so I appreciate it. Good. So you captured. There are two things going on, and you said both of them. The first thing going on is that the exponent, so for example, the 2 here, becomes the coefficient of the derivative, right? So this 2 became again, similarly, the 3 here became the coefficient of the derivative. And the second thing going on is that the exponent, right, in other words, this 2 in the derivative becomes 1. The 3 here became a 2. So the derivative gets lowered by 1, and the coefficient, in other words, the number multiplying the derivative, is the exponent. And you can summarize this nicely by saying that generally the derivative of x to the n is n times x minus, is n times x to the power of n minus 1. And you can see that this is true for all of these cases. So generally the derivative, so d dx of x to the n, again, this is this thing that says this is the derivative. The derivative of x to the n is n times x to the n minus 1. And this is true for all of these things, and on and on and on. So if I asked you, if f of x is x to the 10th power, well, I'm going to apply this property. So n here is 10, and this statement is saying that the derivative is n times x to the n minus 1. So n is 10, so 10 times x, n minus 1 would be 10 minus 1. 10 minus 1 is 9. And soon this will become so second nature to you, you'll just see this. You'll see x to the 10th, and you'll just say, oh, the derivative is 10 times x to the 9. So this is called the power rule, and it's the most famous derivative rule. So this is the example we just did, x to the 10th. Can someone tell me what the derivative of x to the 15th is?
15.
Someone besides Aditya, because Aditya has been participating very well.
15x to the 14th.
Good, thank you. Good, that was very fast. And so you identified n to be 15, and then you put it out front, and you subtracted, to get this 14, you did n minus 1. Good. Can someone tell me what the derivative of x to the negative 5 is?
Negative 5x to the negative 6.
Be careful. Wait, let's see here. No, you're right. You're absolutely right. I always am very cautious of how when the exponent is negative. You're absolutely right. Negative 5x to the power of negative 6. Good. Can someone tell me what the derivative of x to the 10,000th is? Is it any harder? No. Can someone tell me what it is? Someone different?
10,000x to the power of 9,999.
Nice. Good job. Look how smart you are. Good. So this is really, I don't think I had anything else to cover. This is really all I had to cover. I'm glad we could finish in time. It was an ambitious class, and there is a quiz, so I'll send that out in just a sec. But before the quiz, does anyone have any questions about anything we talked about? So understanding how to apply this rule is very mechanical, and it's more important to understand the idea of the limit than it is to really know this rule, this power rule. Sure, it's powerful, no pun intended, but I really want people to understand the theory behind this. What is the derivative? Here's the formal definition. Sorry, I'm zooming in the wrong direction. This is the formal definition. This is what I really want you to understand, right? we can also use this definition if you like. So does anyone have any questions before the quiz? We talked about a lot. We talked about things that are differentiable, things that are continuous, the relationship between differentiability and continuity. Any questions? People, you're learning calculus, okay? So this is not like light stuff. The stuff we've been covering in the course is definitely light compared to the stuff that you're facing today. So it's okay if you're confused. It's okay if sort of you have lots of questions and are too shy to ask. All the tutors are calculus pros. So literally, you can go to John, Christian. In fact, Christian, Christian does research in calculus. He does research in theoretical calculus. So you can't really go to a better person than him. But Patricia, Anya, we're all calculus people. There is a quiz today, and here it is. Okay, so I just sent the quiz out, and stop recording.